Welcome to The Deep Dive, the show where we dig into the surprising science, the hidden stories behind everyday things, hopefully giving you some really actionable insights.
That's the goal.
And today, we're cracking open the secrets of something pretty much everyone loves, the cookie.
Ah, yes. The cookie.
You might think baking is, just mixing stuff together, but this deep dive into a really fascinating study is probably going to blow your mind a bit about how one tiny change makes all the difference, especially with whole wheat flour.
It really does. And it's a question that seems so basic, right? What makes a cookie perfect?
Ah.
But the answers, as we're about to find out, are, well, incredibly nuanced and surprisingly scientific.
Yeah.
So our mission today is kind of cut through that kitchen confusion, and show how a single variable mixing time seems minor can totally change the whole wheat cookie dough and, crucially, the cookie itself.
Exactly. And we're not just going off like grandma's recipe notes here.
Yeah.
This is solid research. Our insights are coming straight from an academic study called Effective Mixing Time on properties of whole wheat flour-based cookie doughs and cookies.
Catchy title.
Yeah.
Right.
But basically, they took whole wheat flour and mixed it for different times, just 1 minute all the way up to 10 minutes, and watched exactly what happened.
So look, whether you're a serious baker trying to nail that perfect crumb, or you're just kind of curious about why stuff happens in your kitchen.
Or maybe you've just made hockey pucks out of whole wheat flour before, like me.
Possibly. Yeah. This deep dive should give you some really practical takeaways and honestly some proper aha moments about the chemistry and physics hiding in your cookie jar.
Okay, let's lay the groundwork then. Cookie science basics. Every cookie starts with those core things: flour, sugar, fat, usually butter, and water.
The essentials. Then you've got things like salt, maybe eggs, baking powder. The study calls them the icing on the cake. They enhance things, but the foundation is those first four.
Right. And a key player in that flour is gluten. Talk about gluten.
Okay, gluten. It's from the proteins in the wheat. Think of it like tiny elastic bands. They give dough its stretchiness, which you need. But for cookies, it's tricky. Too much gluten development, those elastic bands get too strong, and your cookies end up tough, chewy. Not really that ideal melt-in-your-mouth texture we usually want.
Okay, so gluten builds structure, maybe too much structure. Then butter, the fat, seems like it's working against that. How does it make things tender?
That's a great way to put it. Fat, like butter, gives that tender touch. It literally gets in there and coats the protein strands.
Creates a barrier.
Exactly. It kind of shields them, slowing down how quickly that gluten network can form. That's key for a tender, crumbly cookie. And, obviously butter adds amazing flavor and helps with the shape and structure, too.
And sugar, not just for sweetness.
Nope. Sugar's big for shape and texture, too, especially that creaming step you always see in recipes. Creaming butter and sugar isn't just mixing, you're whipping air into it.
Creating fluffiness.
Yeah, tiny air bubbles. It's a two-step thing. First, cream the fat and sugar till they're light and fluffy. Then you add the dry stuff carefully. Minimum mixing. That aeration is vital. Skip it or do it wrong, and your cookies might spread too much or be dense, flat.
Got it. And then there's chilling the dough.
Huh.
The standing period.
Yeah.
Why do we do that? Is it just making it easier to handle?
That's part of it, but there's science too. Refrigerating for an hour lets the water really soak into the flour, the starch, and the protein.
Okay.
It makes the dough firmer, definitely less sticky, yeah. But it also sort of stabilizes everything, lets the flavors meld, improves the quality before it even hits the heat. It's like letting the ingredients properly get to know each other.
Right. Okay, now let's focus on the star here. Whole wheat flour, WWF, versus the regular white stuff, refined wheat flour, RWF.
Big difference. Whole wheat flour uses the entire kernel, bran, germ, endosperm.
So more nutrients.
Way more. More fiber, antioxidants like ferulic acid, vitamin E, stuff that refined flour, which is basically just the endosperm, is missing. Some studies even suggest refined flour might have adverse health effects long term.
And what about the gluten? Is it different in whole wheat?
It is. WWF actually has quite a bit of gluten, which is why you can roll it thin sometimes. But, and this is key, it makes it more sensitive to mixing time than refined flour.
How so?
Well, refined flour's gluten tends to form stronger, more robust networks. It's actually more forgiving. If you overmix a bit, you might just get a chewier cookie. Whole wheat, it's more temperamental. The bran and germ interfere a bit with gluten formation, making it a bit more delicate. Mix it wrong, and it goes sideways fast.
Okay, temperamental. I like that. And that really tees up the study's main question, doesn't it?
Perfectly. Because even though bakers kind of knew processing mattered, nobody had really zeroed in specifically on mixing time's effect on whole wheat cookies and the dough.
So this research aimed to figure out why sometimes your whole wheat dough feels great, and other times it's like glue or rocks.
Exactly. It's pinning down that why.
All right, let's get our detective hats on. Dough deep dive.
Yeah.
What's happening before baking? They use microscopy, right?
Yeah.
Like powerful microscope.
Yeah, basically zooming way in to see the structure. And at just 1 minute of mixing, they called it MT1,
Yeah.
the picture showed these large, uneven dough particles, meaning it wasn't mixed well, not homogeneous, and the gluten network barely starting to form. The ingredients were still kind of separate, not a good start for a consistent cookie.
But then they mixed it longer.
Right.
Yeah.
And as mixing time increased, things got much better blended, more homogeneous, the crumbs got smaller, more uniform, and here's where it got really interesting. Under the microscope, the dough mixed for 3 minutes, MT3, looked the best.
Best how?
It had the most organized structure, all the components seemed really well distributed, and crucially, the water was spread out most evenly in smaller pockets compared to the other samples.
So 3 minutes. That's the magic number for the dough. Is it that simple?
Ah, if only. MT3 dough looked great, really homogeneous, but the study found if you kept mixing past about 7.5 minutes, things went downhill.
How so?
The dough got stickier, harder, it lost that nice crumbly quality you want, and that's likely due to too much gluten development, making it tough, or even worse, the gluten structure starting to break down, proteins denaturing. It's a really fine line.
Wow. Okay, so the visual structure changed dramatically. What about the water itself? They used something called FTIR analysis. Sounds complicated.
It's basically a way to see how molecules are vibrating and bonding. Think of it like shining a special light on the dough to see how the water molecules are interacting. Are they free or tightly bound up with the flour?
Okay. And what did they find?
Well, first, surprisingly maybe, the total amount of water didn't really change much across the samples. It stayed around 24.5%, which makes sense. Same recipe.
But how the water was behaving changed.
Exactly. The FTIR showed that at longer mixing times, like 10 minutes, MT10, there seemed to be more free water. The hydrogen bonds between water molecules were weaker, but there is still a lot of strong hydrogen bonding overall, probably because the proteins, and especially the fiber in whole wheat flour, are really good at holding on to water tightly.
And did mixing affect the protein structures themselves?
It seems so. They found that longer mixing times tended to make the protein structures less orderly. The main structures were these things called bow-turns and veau-sheets, which give dough elasticity. But the more ordered structures, helices, were barely there. It suggests overmixing might kind of mess up the protein's neat arrangement.
Less organized proteins. So how did all this stuff, the visual changes, the water behavior, the protein structure, translate into how the dough actually felt and behaved, the mechanics?
The texture. They tested firmness and spreadability. The MT1 dough, mixed for just a minute, noticeably less firm.
Which means?
Poor gluten development, weak structure. That dough would likely lead to cookies that just crumble apart too easily friable, is the technical term.
Okay, and longer mixing.
Doughs mixed for 3 and 5 minutes, MT3 and MT5, were significantly firmer. That signaled better gluten development. And they noted these had better overall spreadability properties, too.
But not too firm.
Right. Push it too far, beyond 7.5 minutes, like MT7.5 and MT10, and the firmness went way up. The dough became stiff, not stretchy. Classic signs of overmixing.
They also looked at something called stress relaxation.
Yeah, that's basically how much the dough can kind of absorb energy or relax under stress, how much give it has. Generally, that increased with longer mixing times.
Why would that be?
The thinking is maybe the longer mixing starts to break down the gluten proteins into smaller bits, and these little bits then act like tiny reinforcements within the starch matrix, kind of like adding gravel to cement.
Huh. Okay. And then there was this electrical impedance test. Sounds really weird for dough.
It does, but it's fascinating. It measures how easily electricity flows through the dough. High impedance means it's resisting the current. Low impedance means it flows easily.
So what did that show?
The MT1 dough, the undermixed one, had the highest impedance. It was resisting the current, likely because it wasn't uniform. It was inhomogeneous.
Makes sense.
But here's the cool part. The MT3 dough, the one that looks so good under the microscope, It had the lowest impedance.
Meaning it was the most conductive.
Yeah, suggesting it was the most consistent, most uniform water flour system. The idea is the dietary fiber in the whole wheat flour combined with water formed ions, making it easier for the current to pass through. Lower impedance, more uniformly mixed dough.
So MT3 really was the champion, at least for the dough stage.
Right.
Most homogeneous, lowest impedance.
Exactly. Based on the dough analysis alone, you'd probably pick MT3.
All right. So we've mixed, we've rested, we've poked and prodded and zapped this dough. Now, the moment of truth. Baking time. Let's unpack the actual cookie. What did they look like?
This is another surprise. Despite all those big differences in the dough stickiness, firmness, impedance, the baked cookies, they looked remarkably similar. Yeah. Same light brown color, that typical browning at the edges, the surface cracking you often see with wheat flour cookies. Visually, mixing time didn't make a huge difference.
And what about size and spread?
Also surprisingly consistent. Statistically, there was no significant difference in width, thickness, or the overall spread ratio across the different mixing times. So a 1-minute mixed cookie looked pretty much the same size and shape as a 10-minute mixed cookie.
Okay, that is unexpected after hearing how different the doughs were. What about moisture inside the baked cookie?
Moisture content ranged from about 11% to 13.5%. Interestingly, the MT3 cookies from that perfect dough actually ended up with significantly higher moisture than cookies mixed longer, like MT7.5.
Why would that be?
Probably down to that high fiber content in whole wheat flour. The well-developed structure in the MT3 dough might have held on to water more effectively during baking.
And the bonding. Did they check the water bonding in the baked cookies too?
They did, using FTIR again. And this is crucial. The MT5 cookies mixed for 5 minutes showed the strongest hydrogen bonding.
Stronger than MT3.
Yes. Indicated by the highest intensity peak for the OH stretch. This suggests a really stable internal structure in the MT5 cookies. The water and everything else were very well integrated at a molecular level after baking.
Okay, MT5 showing strength after baking.
Yeah.
Now, the texture, the eating experience, hardness.
Hardness generally went up as mixing time increased. MT1 cookies barely mixed were the softest.
Okay, that makes sense.
MT3 cookies were significantly harder than MT1, but then here's the twist.
The plot thickens.
It does. The MT5 cookies actually showed a remarkable decrement, as the study put it, in hardness compared to MT3. They were softer than MT3 and notably more consistent in their texture.
Softer than MT3. Interesting. What about MT10?
By MT10, hardness went back up again, ending up similar to MT3. So it wasn't just a straight line from soft to hard. There was this dip at 5 minutes.
Wow, okay. And fracturability, how easily they snap or crumble.
Right, brittleness, basically. MT1 cookies were the most fracturable, very crumbly. As you mix longer, they generally became less fracturable, less brittle.
So MT3 and MT5.
They had similar fracturability values. But, and this is a really key detail, the fracturability of the MT5 cookie was significantly more reproducible. Meaning batch after batch, the MT5 cookies broke with the same amount of force. They were consistent. You knew what you were getting. The other mixing times showed more variation.
Okay, so let's pull this all together. We've gone from dough microscopy to cookie crunch. What's the big takeaway for someone wanting that perfect whole wheat cookie?
The big takeaway is that mixing time is huge. It affects the dough profoundly and the final cookie texture, but not always in a straight line. It's complex.
And the sweet spot.
The study concluded that for these whole wheat cookies, using their method, which included 5 minutes of creaming first, a mixing time of 5 minutes MT5 gave the best results overall.
Even though the MT3 dough looks more homogeneous?
Exactly. While MT3 dough had that optimal structure initially, the MT5 baked cookie delivered the goods. Good texture, strong internal bonding, and crucially, that excellent reproducibility, especially in how it fractured, that consistent snap.
So 5 minutes of mixing seems to be the winner for the final product you actually eat.
Based on this research, yes. MT5 hit that sweet spot.
You know, this whole deep dive, it really isn't just about cookies, is it? It's about seeing those incredibly intricate links between a process, even a simple one like mixing, and the final outcome, right down to the molecular level.
Absolutely. It hammers home that mastering something isn't just about having the right ingredients. It's about understanding how you process them, those subtle variables like time, temperature, technique. They have such a powerful impact.
It makes you think, doesn't it?
Yeah.
What other seemingly simple things in life, you know, whether it's cooking or a hobby, maybe even stuff at work, might have their own hidden scientific sweet spot.
Yeah.
That one little adjustment that, if you found it, could totally transform your results.
Yeah, where else does that precision in a small detail lead to those big, consistent wins? Something to definitely chew on.
Indeed. Until our next deep dive.